So Professor Cohen is busy today.
Yes, I know that.
He has a meeting, so I will give you the last lecture of this English one course. We continue the previous lecture with some remarks on the conversion of power series. In the last lecture, you have learned the definition of power series. So you can see this notation of the power series about x equal a, and you have the usual form of a series. Let's take a look on some remark on the conversion of a power series. The first one, for each fixed value of x, because a series, it is a series of numbers, right? So that means you may apply the test for conversion or the test for diagonal. That we have learned in the previous lecture. The power series may converge for some values of x or diverge for other values of x. So in the next part we will see how to determine the values of x that make the power series converge. When the power series converges, then the sum of a conversion of that the conversion power is a function of x, which is fx. That means for the value of x, if your power series converges, then you can assign a value for that series, and we can define a function f. About the conversion, you have three possibilities for power series. The first one, the power series converges absolutely for all x. That is the first possibility. The second case, the power series converges only at one point and diverges elsewhere. Only one point. And the last case, there is a positive real number r such that the power series converges for the absolute value of x minus a is less than r and diverges for the outside of this circle. You know, this represents the outside part of the circle, right? With the ball, with the center A and radius R. You know. So we know that a power series may have one of the three cases about the conversions, and now we will define the radius of conversion and the interval of conversions. So let's take a look on the first case, where we have a number r. Then that number is called the radius of conversion of a power series. So this is also the definition of the radius of convergence. Then with this definition, you can see the first case and the second case are the special case where for the first case the radius is infinity because we have conversion for all of x, you know, then the radius of conversion is infinity. While for the second case, when the power series converges only at one point, that means the radius of conversion should be equal to 0. And the interval of conversion is interval contain all value of x for which the power series converges. So very logical definition. Is better presentation, interpretation about the interval of conversion corresponding to each radius of conversion. When the radius is infinity, then the interval of conversion is from minus infinity to infinity. When r is 0, then the interval of conversion is only one value of a. So for finite value of r, the interval of conversion is one of the following intervals. You know, from the definition of radius conversion, you know the power series converges for every x such that the absolute value of x minus a less than r, right? So that, okay, so that means, that doesn't mean, okay, so sorry, the power series converges for x minus r less than r, and the absolute likewise for x of that, the absolute value of x minus a greater than r. So we have no information when x minus a to r, right? That is the reason the interval of conversion might have one of the following form. We cannot exclude about the conversion at the end point. Right? So we will see that later. Okay, so in the previous lecture, you have learned the power series, right? The power series of this function. And that has radius of conversion I to 1, and the interval of conversion is from minus 1 to 1. And in this case, this power series diverges when x equals 1 or minus 1. We exclude the endpoint. Right. Now we will see how to find the radius of, and the interval of conversion. You will see we have okay, so 2 steps. Okay, so let's go to the first step. So you know when we fix fix the value of x, then a power series becomes a series of number, right? That is the first remark. Then we can use any test for conversion or diversion. So that means we can use the root test, radial test, or okay. So you know from the last lecture you've also learned about the integral test, limit comparison test, right? So let's choose an appropriate step to give you a view about the conversion of a power series. Of course, the test depends on the power series. So, in this first step, you are able to define the radius of conversion. Then, there may be one of the three cases. If you find the radius of conversion which is infinity, then we conclude that the power series converges absolutely for all of x. That is the first case about the conversion theorem. And when you find zero value of r, your power series converges only at one point, x to a. If the first case happens, that means r is a finite number, finite positive real number, of course, right? Then we need to do a little bit more to determine precisely the interval of conversion. Okay? Because as I said before, we have no conclusion about the conversion at the endpoint, where we have the absolute value of x minus a equal to r. Okay? We need to check it separately. That is the second step, determining the conversion of the endpoint. Okay? So when you substitute x equal to the endpoint into the series formula, you have a normal series of numbers. Then you can use test for conversion or divergence. Okay? That is two steps to find the radius of conversion and interval of conversion. Now we will take a look on some example to see it clearly. Okay, so here's the first example. We consider this power series about zero, right? For this power series, a equal to 0. So let's come to the first step. So let's observe this series as a normal, a series of number, because we fix the value of x. Okay. Then you see with this type of element, we should use the Rayleigh test or the root test, right? So let's use the Rayleigh test to determine the radius of conversion. Okay. For the Rayleigh test, we should consider this limit, right? So here is the AN, the general formula for the element of the series, right? Then you can find, using this definition, you can find it clearly. This ratio, AN plus 1 and AN. Okay, so we are going to find this limit. Okay. Okay, so D2 transformation is standard, right? Using the formula, the even formula of the series. So in the final step, you can see we have this. In fact, AN plus 1 over to AN equal to this. Right? And now you see we consider x as a constant number, so we can put it into the outside limit notation. That is the reason we have this expression. Okay? And this limit is easy to calculate, right? It is 1. So the limit in the ratio dash is a number depending on x. Do you agree? So let's compare with the possibility of in the conclusion of ratio dash. You can see here with the fixed value of x, if this limit is less than 1, then this series converges. Right? That is the conclusion in the ratio dash, and diverse for the value of limit greater than 1. So you see that we already find the radius conversion, right? This power series converges for all value of x such that this inequality and diverges outside the wall with the origin 0 and the radius 2. Right? That is exactly the definition of a radius of conversion. You can compare it with the definition. So we finish the first step by saying the radius of conversion is 2. Okay? And keep in mind that our series is a power series about 0. That means a equal to 0, right? So we need to do further step to verify the conversions at the endpoint. So now the endpoint is x equal to and x equal to minus 2, right? That is what we are going to do. We will evaluate the conversions of the power series at x equal to and x equal to minus 2. You just need to substitute the value of x into the formula of the series. Then you will get this normal series. And after calculating, you get this harmonic series, right? And we know that from the last lecture, this harmonic series diverges. So it is important to remember some conversion results for important series. Harmonic series, P series, or alternating series. It doesn't have to define quickly the conversion or diversion of a normal series. Okay. So you agree that at x equal 2, the corresponding series diverges. That means the given power series diverges at x equal 2. So we will exclude this point to the interval of conversion, right? At x equal to minus 2, then we have this alternating series. This alternating series satisfies that the sequence of element Bn, which is 1 over n, right, decreases to 0. That is the alternating series test, right? Okay, so I just remind you about the alternating series test, and that concludes the conversion of the given power series at x equal 2. Okay. So now we have all information about the conversion at the end point. So we can conclude the interval of conversion. And you can see here is the interval of conversion, right? Where we take the value x equal to -2 and remove the point x equal to 2, right? And the radius of conversion is r equal to that is an example of how to find the radius of conversion and the interval of conversions. So you can take a look at this remark. In the first step, we can use also the root test. That means we need to consider this limit. Okay. So depending on the form of the power element of the power series, you need to decide relevant test for conversion, ratio or root test. There are the main tests for this type of problem. Using the same idea, you are able to consider the two examples. So, for this power series, we need to find the radius of conversion and the interval of conversion. Let's see which type of test we should use for the first step, ratio or root test. So we have an equal to x power n over n factorial, right? Factorial. I think for this type of series, we should use the ratio test, right? Because we have this notation of n factorial, the product of the first and integer number, right? So if you use the ratio test, you should consider the limit of an plus 1 over an, right? That will give you okay, so x multiply with okay, so over n plus 1, right? So you can see that the absolute value of it equal to x over to n plus 1 and it tends to 0, right? That means for every value of x, this series converges. You know? By the ratio test, when the limit equals to 0, then the series converges absolutely, right? This limit does not depend on x. That means for every x, we have the conversion of the series. So the radius of conversion should be infinity, right? And in this case, we can easily conclude also about the interval of conversion. For the second example, okay, so we have this series, and now an has this form, and factorial multiply with x minus 1 power n. So for this series, again, you see a factorial. So I suggest you to use the ratio test. The ratio test means we should consider this ratio, and it is n plus 1. So, okay, so multiply with x minus 1. You see? And this ratio tends to infinity. And this value limit does not depend on x. So you can say that for every x, the series diverges, right? Because the limit is infinity, then using the ratio test, we know the series diverges, right? I mean, for every x, the series diverges. That means the radius of conversion is to 0. And this series converges for only one point, x equal to 1. Okay? Sorry that I should include the information that x, when x is not equal to 1, this limit is always equal to infinity. Right. So the interval of conversion is only 1 point. X equal to 1. Okay? So there are examples of how to evaluate the radius of conversion and interval of conversions. So now we are going to consider some important property of the power series, which converges. Okay. So when you look at a power series, you may ask a question: can we differentiate it, right? Because when the power series converges, it basically is a function. So we can ask a question about the differentiable, right? Differentiability. So here is the answer. We suppose a power series converges of this form. Okay, converges for x is satisfied in this interval. You can see that that means R is the radius conversion, right? Then you can differentiate this power series term-wise. Okay. Now you can take a look on this formula to see what differentiates term-wise mean. So if we take the derivative of this even power series, then you can do it term-wise. Okay? That means you differentiate term by term. Okay? So you can see just the knowledge about the differentiation of a power function. Okay? And opposite this differentiation power series also converges for x satisfying this condition. Okay? Sometimes this theorem will help you to determine to calculate to determine the power the power expression of some function. You will take a look on. Okay. Before going to some example, we will consider the higher order derivative. So in this theorem, we already considered the first derivative, right? We can do the same for the higher order derivative. Here you can see an example of second order derivative. Okay. That means if you want to take the second order derivative, you should take the derivative of the first order one, right? Yes. And using the previous theorem, you have this first order derivative of power series, right? And you do the same calculation one more time, you will get the second order derivative power series. Okay. So that is about the differentiation. And now we will see the very similar result for the integration. Okay. That means now you can integrate the conversion power series to get a new series. We suppose that the given series converges for this radius, for this interval convergence. Then it can be integrated termwise. That means if you want to integrate the power series, you can integrate each element of the power series and sum them up. You can see here it's a given series and we integrate it. You just need to consider this corresponding integration power series. When you integrate each element of the given series. Right. And you know, this formula is very familiar. That is the basic integration of a power function, right? And this new power series also converges in this interval x. Of course, we should not forget this notation of a constant number, right? Because we are considering the indefinite integral, so we should keep in mind that this notation of arbitrary constant number. Okay, so let's take a look on this example to see how to use the power series to find how to find the derivative of power series and yeah. So we are given this function f with the power series. It is very well known from the last lecture, the previous lecture you already saw it, right? This series is convergent for a satisfy this. So the radius conversion for this power series is r equal 1, right? So in the first part, we need to find a power series of the derivative of f, first order derivative of f. Okay. So you see, that is what I said before. This series has radius of conversion 1. That means it converges absolutely for all x belong to this interval. Okay. So with the formula fx equals 1 over 1 minus x, you can find this. You can find this first order derivative easily, right? So here's f prime x by using normal calculation. Now we use a previous result to calculate the corresponding power series of the first derivative f. So we do this termwise, right? We take the derivative of this series termwise. That means we differentiate each element of the power series, and you get this this term of the new series, right? So you agree? I think it is very simple, right? It's just the precise form of the power series. I hope that notation of summation is well known for you, right? And this one is just a precise form of this notation, nothing more. So we have the power series representation of the first order derivative of f. See, in the first step, we already find this formula for f prime, and in the second step, we find this formula for the derivative of the power series, and we have the equality. That means the first derivative of f can be represented in this form, and this formula is true for x less than 1 and greater than minus 1. Okay? Because you know this how to say this formula is only true in the interval of conversion, right? So outside of this interval is not true anymore. Right? We can only represent this function into this form for x belong to this interval. That is very important to remember. So that means you see for this function you have this power series representation. Right? That is also the proof of proving this representation for this function. So that means if you are asked to find the power series representation of this function, you might think about using this method of differentiation. Okay? So in the part B, we are asked to find the power series of the function, of this function. That is what I told you before. If they give you a function and ask you to find the power series representation, you might think about using the differentiation of a power series. That means you are given this function. You might think about this function is a derivative of which function? Okay. And do we know about the power series representation of that function? That is the main proof. Okay, so let's take a look at it. So if you continue to differentiate this function, you will get this one, right? Do you agree? If you use the normal calculation, you can find the derivative of this function. It is also the second order derivative of the given function f, which is 1 over 1 minus x, right? So that means if you want to find the power series representation of this function 1 over 1 minus x power 3, you need to use the power series representation of this function, which we get from the previous step, right? So we differentiate this series stepwise one more time to get the second order derivative. Okay. So you will get this new series. And in the long form, you get this representation. And if you divide this series by 2, you will get the function 1 over 1 minus x or 3. Right? That is this 3, right? Okay? That is how we use the differentiation of a power series to determine the power representation of a function, a given function. So you can think about finding an antiderivative of a given function and see that if we can find the power series representation for that antiderivative, okay, then you can just need to differentiate the power series to get the result. We can use the same idea for the integration of power series. Okay, so take a look on this example. So we are going to find the power series of this given function for x belong to this interval. So now we take a little bit different from the previous example. We will see if there is a function. We will take how to say. We take the derivative of this given function to find its derivative, and observe that if its derivative can be represented in the form of a power series. If yes, we can use an integration of power series. That is what we are going to do now. You can see that the derivative of the given function is 1 over 1 plus x, right? Equivalently, if you integrate this function, you get the original function, right? That is a basic integration. And you know, for this function, you have this power series representation, right? It's very well known, right? That means if we integrate the both sides of this power series, we will get the power series representation of the given function. Yeah, you can see we integrate both sides of this identity, then we get what we want. So we also do the integration term-wise. Okay. You see, we calculate this integration power series term-wise by integrating each element of the power series. So it's not difficult to calculate this result of this integral, right? Then you will get this power series representation. But yes, we need to determine the constant number c. It's very easy by substituting x equal to 0 into this formula. You will find the value of c. And here c equal to 0. That means you have this power series representation of this logarithmic function. So that means depending on the given function, you need to choose one of the two type power series. They are the differentiation or integration. So in summary, you obtain the power series representation for the function. And I think for the three function, you should remember this the power series representation. And you can use the result for the function without proving again. Okay? But be very careful with the interval conversions. That means the formula are true for x only for x belong to the interval of conversion. Okay. So that means you cannot use this formula for x equal 2, right? Okay, so we move to the next topic. Now we will see so in the previous part of this lecture, we have seen that we can define a function from a power series, right? Now we will see a reversible observation and a very very natural question. If we are given a function, can we define a power series? Okay. That means now we are given a function. Can we define a power series which we expect to converse to the given function? That is a reversal observation comparing to the previous part of this lecture. Okay. So you can see this theorem. If we are given the function f has a power series representation of the x equal to a, so you can see here we already have the three examples of function f, right? Which has a power series representation. Then f is rewritten in this form of power series, and we can calculate precisely the coefficient Cn of the power series by using the derivative of f. So you could try to verify this formula by using the three power series representation. Okay. Here are the Cn. For example, the first power series C0 is 1, C1 is 1, and C2 is 1. And Cn are equal to 1 for every n, right? For the second power series, C0 is 1, C2 is minus 1, and C3 is 1. You can try to calculate the n derivative of this function. to verify this formula. Also, we will see how to get the formula of the coefficient now. So from the assumption, we know that we have this identity, right? Because the function f has a power series representation mean, we have this equality. We just substitute x to a into this identity, then you see that except the zero order term, all elements are equal to 0, right? That means when you substitute x to a, this infinite sum contains only one term, which is fa, c0, right? Because this one is nothing but c0 plus c1 x minus a, c2 x minus a squared, and so on, right? And when you substitute x to a, only this term last, right? That means we have fa equal to c0. You agree? Okay, so we find the formula for the c0. So to find c1, we need to differentiate the function. Okay, so let's consider the first derivative of f, and from the previous property of the convergence power series, you know you can find this power series, the first derivative. You can differentiate the given series term-wise to get this formula, right? And be careful, because this series starts from n equal to 1, because now we don't have c0 anymore, right? And the 0 order term now is correspond to n equal to 1. That means the 0 order term is 1 multiplied with c1 multiplied with, okay, 1 multiplied with c1, and equal to c1, right? And then if you substitute x equal to a into this power series, you will get this coefficient c1, and it is equal to the first derivative of f at the a. Doing similarly, you can find c2, and in general, by induction, you can find ck. Okay. You know that when you differentiate one time, the degree of the polynomial decreases by 1, right? That is the idea to how to find the general formula for the coefficient of power series representation. Okay, so this is the precise form of the coefficient when the function is assumed to have a power series representation. Okay? So now we will take a look on this, on the, how to say it. So if we are given a function, but we don't know if it has a power series representation. We want to define a power series for it, right? Now we are going to do that. Keep in mind that now we don't know if our function has a power series representation or not, right? So we start with the definition of the Taylor series. So to define a Taylor series generated by a function f, at x equal to a, we need to assume that the function f has all derivative of all order. You can see easily one example of this function is exponential function, right? Or the exponential function, e power x or a power x. You agree? Z function has all derivative of all order, right? In fact, e power x prime is itself. It doesn't change. So we define this power series and we call it the Taylor series. If we want to define a power series, we need to define the coefficient of the series, right? So we define a power series with the coefficient of this form. The coefficient of x minus a power n term is defined by the n derivative of f of a. We can determine this value because we already assume f has all derivative of all order. So it makes sense, right? So keep in mind that this is just a definition. Okay? It's not a theorem or something else. It's just the definition. A power series defined in this way is called the Taylor series generated by the function f at x equal to a. So if you are asked to find the Taylor series generated and you are given a function, let's calculate all the coefficients and use this formula. Okay. And we have a special case when the point A equals to 0, then this series has a name, has another name, and we call it the Maclaurin series. Okay. That means this special series, the Maclaurin series was right before the Taylor series. That is the reason it has the name of this mathematician. So the Maclaurin series is nothing but the Taylor series for a equal to 0. Okay. Okay, so you can see here an example of the problem of finding the Taylor series of a function, of a given function. So we are given this function f and the point a equal to 3, and we need to find its Taylor series. Okay? So, as I said before, you only need to determine the coefficient of the power series, right? And here's the formula. Okay? So, that means we need to find the formula for the n derivative of f. And here's how we do it. So fx is 1 over x, f prime x is minus 1 over x squared. f2 prime, the second order derivative, is this one and can be rewritten in this form. So in general, we observe the n derivative of f has this general rule, right? We can, I don't see other way to find this general formula. You need to observe it more often, and you will get the rule. And of course, to to have this formula, we need to use the induction method to prove. Okay. We observe some first term of the derivative. Then we conject a general formula, and we need to prove that. And how to prove? You can use the induction method. But the most important point is to guess this general formula. Okay. So you know, when you find the coefficient precisely, you already define the power series. Okay. So you can see here the Taylor series generated by this function at a equal 3 is written in this form. Okay. This remark is about using the ratio test to find the radius of conversion. Okay, so if you have this power series, you may ask about the question. You may ask question about the radius of conversion and interval of conversion, right? We define a Taylor series by using a function f. It doesn't mean the Taylor series converts to the given function. You know, we only use the derivative of f at a to define a power series. Okay, but that series might not converge to the function f. You should be very careful with this definition. Okay, so for given a function f, you can define a Taylor series. However, this Taylor series might not be conversion to f. Okay, that is the reason we need to observe, to evaluate the conversion of the Taylor series as we have done in the first part of this lecture, using the two-step. First step using the ratio or root test to determine the radius of conversion, and the second step we need to evaluate the conversion at the end point when after finding the radius of conversion. And you can see here the ratio from okay, so the common ratio is this one, and we want the absolute value of r is less than 1 to have the conversion of the power series. That means the radius of conversion now is 3, right? The Taylor series conversion absolutely for every x satisfies this condition from the ratio test. Yeah, you can see it here. The series converges absolutely for x satisfies this equality. And for x satisfies this condition, you might write okay, so you may write f in terms of Taylor series. You know? Here's some important remark for this, in some sense, I already told you about the remark before. So you can see the first one. In general, the Taylor series generated by a function may or may not be fx. Okay? It's very clear that we only use the information about the derivative of the function f to define a Taylor series. But it doesn't mean the Taylor series converges to the same function. Okay? But the first theorem in this part tells us that if f is representable as a power series, then the power series is Taylor series. Okay? So come back to the first theorem. We know that if a function f has a power series representation, then that series is nothing but the Taylor series. You can see that by looking at by comparing the coefficient of the Taylor series and the series given in that theorem. And many functions have power series representation. I showed you before 3 important functions, right?
Yes.
However, there exist functions that are differentiable but has no power series representation. Okay? Okay, so we have seen the Taylor series generated by a function. Now we have a new object to look at. That is the so-called Taylor polynomial. That means we take only the sum of the first n term in the Taylor series, and you know that is the partial sum of the Taylor series, right? You can see in this formula we take only the first n term of the Taylor series. Okay? Here's the first term and here's the n term to get the Taylor polynomial. And now look at this polynomial. You can see this is the highest order term, right? That means this polynomial has degree n. Okay. So the Taylor series, Taylor polynomial T and X is defined in this way, and it has degree n. So it is also the partial sum of the power of the Taylor series, right? This Taylor polynomial is very important in the problem of approximation. Okay. We expect that when n tends to infinity, the limit of Tn converges to the limit, the value of the function f. Of course, we at the same point x, right? Okay, so we have here some notes on Taylor polynomial. Okay, the k derivative of Tn and fx have the same value at x equals to a. So you can verify this statement by looking at this formula. That can be considered as exercise for you. So in the part B, you have here the linearization of F A. Okay. This linearization is the first simple method for you to approximate a value of a function, right? That you have learned, and it is the first Taylor polynomial. You see. So you see this linearization help you to approximate the value of fx, right? So in practice, sometimes you only have information of the value of fa and the rate of change of f. So you may use this linearization to approximate or guess the value of f at x. For example, I can show you a simple example. So the problem of considering the population is very important, you know, and the data is gone. Is you only know the least information. That means you know the population of the first year. You know the information about the population of the second years and the third years, for example, and you want to guess the population in the fourth years. You don't know, right? But we want to have a guess on the value of population. So how we use the information on previous year to guess the value of population in this year. Okay. So we denote the function f, which is the population. X is the value of the years, and we know f1, f2, right? f3, and we want to get the f4, right? There are two things we might get from the data. You might see the rate change f, right, by looking at a graph or comparing the value of f1, f2, f3. You might have the rate of change of the population. That means you have information about f prime a, right? And for example, you know f prime 3, and you already know f3. So you have you can get you have this linearization Lx equal to f3 plus f prime 3 x minus 3. And if you want to find the f4, you only need to substitute x equal 4 here. That gives you an approximation about f4, but we don't know the formula of the function f, right? Just remind you a little bit about the approximation, the importance of the approximation function in practice. So forget about it. You only need to remember that for this simple application, they use only the first degree Taylor polynomial T1, right? And T1 gives you a method to approximate the function. So you might think that if we increase the degree of the Taylor polynomial, we will get a better approximation method, right? So you can see that when n equal to the second order Taylor polynomial has the name of quadratic approximation. Okay. That means using this one you will get a better approximation method. So you can see here this formula of Taylor remainder answer show you more clearly what I have said before. So if I have a function f which has a derivative of all order in an open interval that contain the point A, then you can approximate the value of f by the n Taylor polynomial, and this one gives you the remainder. Okay. We need to remember this formula, and we denote Rn by this one to be the Taylor remainder of order n, or the error term for the approximation of f by Tn. So keep in mind that we have a constant number c here. Okay. C is fixed number. However, we don't know the exact value of c. We only know that c is some value between a and x. Okay. In fact, for each value of x, we have cx. For different x, we have different value of c. So this remainder term is very important to see how good is approximation method by using the Taylor polynomial. Okay. So you see, that means, okay, so let's come back to the problem of power series representation. I told you that when you have a function f, satisfy that f has all derivative of all order, then you can define a Taylor series, right? But you cannot write fx equal to its Taylor series, you know, because in the previous remark, the first one tell you that the Taylor series may or may not be equal to the function f, and we are not able to write down fx equal to its power series. That is not true in general. However, we can write fx in this form. You know, we can represent fx in this form. It's nothing but a finite sum, and it is equal to t the n Taylor Taylor polynomial plus the remainder term. Okay. fx equal to this representation, but this one is not a power series representation, just normal sum, right? Okay. Yeah, you can see here. We can take a closer look on the Taylor series of f and how to approximate and how can we expect about the conversion of the power series or Taylor series to each function. So here is the formula represent the function f in terms of Taylor polynomial and order remainder. And we wish to know whether the function f is the limit of the Taylor polynomial. If we have this, that means the function f has a power series representation, right? You agree? Because as I said before, t and x is nothing but the n partial sum of the Taylor series, right? And we know we define the value of infinite series by taking the limit of the sequence of partial sum, right? And then if you have this, that means fx equal to its power series. Okay? And we have this theorem for the power of Taylor series representation of a function. So if we have the limit of the remainder equal to 0, so we fix x and we less the order of the remainder, which is n tend to infinity, and if we have it equal to 0 for all of x, then fx can be represented in terms of Taylor series. Okay?
Yes.
Yeah, you can see more precisely this statement. If the limit of remainder term tend to 0 for all of x, then f is equal to the sum of its Taylor series. Okay? That means if this limit is non-zero, so the function f it cannot be rewritten in the form of Taylor series. That is the case may not in the first remark. Okay, you can take a look on this example. See, this one is a very well-known formula, very well-known power series representation of this exponential function. Okay, it's very well known. So we want to prove that. Okay, so we are given this exponential function, and you can define its Taylor series, right? The Taylor series of the given the exponential function is this one. And it is very easy to verify. But we don't know if we have this equality, right? Now we need to check it. Okay, so here the power series about 0, so it's called also the Maclaurin series, right? So here's the remainder term. Just use the formula you have in the previous theorem. Okay? The n order remainder term has this form, where c is a value between 0 and x. Now we fix x, okay? And we want to observe the limit of this number when n tends to infinity. If this limit is 0, then we have the equality. Okay, so it's just problem of evaluating the limit. So we just consider the one case when x is positive. we have this inequality, then we have this order of e power c and e power x. It's all about the estimation of the remainder term. That means you can bound this remainder term by this number. Okay? You see, now x can be seen as a fixed number. So e power x and x power n plus 1 is a fixed number. Yeah. And x and e power x is a fixed number. And if we let n tend to infinity, you will have zero limit, right? Is this correct? It's not obvious to see this conclusion. We need to use further method to get this limit. Okay, so in general, I just want to say that we can prove the limit of remainder term tend to 0. That means we have this equality. So the only thing I want to emphasize for this problem and for the Taylor series topic. So let me remind you one more time. We are given a function e power x, right? And we can define its Taylor series by calculating the coefficient. And we want to verify that e power x equal to its Taylor series or not. Okay? You agree? If we want to have this equality, we need to prove that the limit remainder, Taylor remainder equal to 0. That is all we need to remember. Okay. So the second application is error estimation. Okay. Of course, the remainder term gives you the error of the approximation, right? And you want, in some sense, you always want to see how big is this error. And then the object to estimate again is the Taylor remainder. Yeah, you can see the Taylor remainder provides the error in the estimation. Okay, that leads to this type of problem. Calculating the error when you use the Taylor series to approximate the given function. And they will precise the order of Taylor series. And you need to calculate the corresponding error. We are given function e power x, and we use the first order Taylor polynomial to approximate the given function. And now, what is the error? Okay. What is the error when x equal to 0.5? We need to see. You can see here, we use a t form to approximate e power x, and here is t form. The sum of the first four first term in the Taylor series, right? So, more precisely, you have T4 at 0.5 is approximately equal to this number. Okay. And here's e power 0.5. And we want to see the error. The error of this estimation, this is an estimation, right? If you want to find this value, and you don't have any calculator, you can approximate it by this value. You know that you can calculate by hand this polynomial, right? And that means this one is hand can be done without any critique, right? But we want to see if this value is correct. How correct is this value? That means how big is the error in this estimation. And the error when you use this value of function of polynomial is given by the remainder, the fourth order remainder, Taylor remainder up to 0.5. Now this is time to use the formula of the fourth order Taylor remainder to get the value of this one. Okay. So I'm not going into the detail, but this one is the formula of the fourth order Taylor remainder at x equal to 0.5. Okay. And C is a value between 0 and x. That means C is belong to 0 to 0.5, right? In the definition of a Taylor remainder, you know C belongs to 0, x, right? But here we substitute x equal to 0.5, so we have this interval from 0 to 0.5. Okay? So with the information, let's try to estimate this remainder. You can do the calculation precisely, and of course the Taylor remainder depends on C, right? And we want to see the power of e power C. Here C is above by 0.5, so you have this inequality. That means the error of that estimation is given by this number. Depending on the application, you might accept it or not. Okay? Because in some application in a precise machine, this error maybe is not accepted. You agree? Okay, so now we turn to the third application. Okay, so far we have seen that we can use the Taylor polynomial to estimate the value of a function, right? And we also see that we can estimate. We can see the side of the error. Okay, and depending on the problem, you might have some some requirement on how big, on or how small the arrow should be, right? So you know that if you use more and more higher and higher or Taylor polynomial, you have better and better estimation, right? But sometimes, using sometimes using the Taylor polynomial with too big order lead to complication of calculating, right? Because we have more terms to calculate. That is not good in some sense. So we need to optimize the number of the term in the Taylor polynomial, or we need to find a suitable, the best Taylor polynomial to use. Okay. So here's an example. Let's see. Again, we are given. So we are given this number, this famous one, the number e. And you know that this number is given by the value of the exponential function at x equals 1, right? So we can use the Taylor polynomial for the exponential function to approximating the value of this number. Okay. So because e equal to the value of exponential function at x equal to 1, so we should use this Taylor polynomial at x equal to 1, right? And now we need to find the smallest number n such that the error in that estimation is at most 10 power minus 5. That is the size of the error we expect. Okay. So we need to write this Taylor polynomial Taylor series in general form, and we will decide which value of n later. Okay. This is nothing but the representation of the exponential function in terms of the Taylor polynomial and the nth order remainder term, right? So here is the general formula for the Taylor remainder term. For the given function e power s, you can rewrite in this form. And keep in mind that we have here a fixed number c. We only know it is in between 0 and x, right? Now we are going to use the information about the sign of error to determine the value of n. Okay? So we first need to calculate Rn, the value of the remainder Taylor remainder at x equal to 1, right? Because we want to estimate e power 1. So here's the precise formula for Rn1. And we want this error is less than or equal to 10 power minus 5, right? Yeah. Okay, so you should take a look on the step yourself, and you can see that we have this estimation if n is greater than equal to 8. Right. That is what we want. That means for n equals to 7, the error is bigger than this order. So the best number of the order of Taylor polynomial in this case is 8 order, n equals to 8. Okay, you only need to use the Taylor polynomial of order n, of order 8 to get the acceptable error in the estimation. You don't need to use you don't need to use a higher order Taylor polynomial. Okay? It's a waste of calculation. Right. Okay, so that is all for today. So let me finish the lecture here. Thank you. Professor Coy have something to say?
So, sorry that I lost my voice. That's why I asked Dr. Lung to conduct the last lecture. First of all, thanks Dr. Lung for his generous agree for conducting. So now, the last some minute, I would like to tell you the following. First, as Dr. Hung said, this is the last, and you see the last lecture, the last chapter, which also means that all the things from chapter 1 to chapter 6 you have to revise for the final exam, which will be on 5th of February. The first week, the end of the first week after you return from your Lunar New Year vacation. And the percentage of question, because we have the first midterm, the midterm already covered 3 chapters. Then, in the final exam, 70% will be on the last 3 chapters. 30% for the first, because we have already the midterm. So, in roughly speaking, not exact 30 or 70, something like that. Okay? So you have also last week we already announced your midterm result, and this result is raw result of midterm, which means that without the bonus point. So after this week, the last week for tutorial, all 4 tutors will be adding the bonus point to you. Right? Then you have the final result for CA, continual assessment, which consists of the midterm point and bonus point. It's 40%, right? And 60% will be the final exam. Okay? So any question? No? No. So I attended the Dr. Lung lecture sitting behind, and I noted, yeah, it is quite normal for any lecturer, a part of students look at the screen, look at the laptop with the real lecture, and the other playing. So it's quite normal, no problem. But nevertheless, I would like to thank all of you, both attending my lecture and sitting in the hall playing other things, but at least attending this auditorium for your attention, at least for your attendance, for your attention, and most of you for your visiting our lecture, my lecture, and Dr. lecture. And I hope to most of this batch, maybe about 500 or 400. So I hope I will be seeing you again. Yeah, but not for Calculus 1 next year, for Calculus 2 next semester. Okay? And I wish all of you to have a success exam, not only for calculus, but also for the algebra and other subjects for this first semester. So, thank you.
Wish you have the best Lunar New Year. I would like to say Happy New Year to you and wish you have the best Lunar New Year with your family and friends.
Vỗ tay.